Welcome students. Today I will discuss the second part of EM induction, electromagnetic induction. So before going to the new part, first I want to discuss once more related with the first part. So what is the fact related with electromagnetic induction? We know that when current passes through any conductor, then it will produce magnetic field. Magnetic field around it, like this. So the reverse concept is, if magnetic field is applied, then current will induce. So this is known as electromagnetic induction. And in electromagnetic induction, we have to establish relative motion between the magnet and coil. Then we can find out the induced EMF. And this experiment is performed by Faraday, that we know. And from this experiment, we have received two fundamental laws of Faraday's. First one, if magnetic flux related with a coil changes with time, then EMF will induce. If magnetic flux related with a coil changes with time, then EMF will induce. So this is the cause of EM induction. And the second one is, the magnitude of induced EMF is directly proportional to the rate of change of flux. Differential. That is D proportional to differential. E proportional to differential. Now these are the laws given by Faraday. So first law, we get the concept, what is the cause of EM induction. From second law, we get the magnitude of induced EMF. But what is the direction? That is given by Lenz. So Lenz law. Lenz law. And what is Lenz law? Lenz law means E equal to minus d by dt. Means whenever we want to introduce a magnet, the pole will be induced in such a way that it can resist the motion of the magnet. What is this? That this is the coil where galvanometer is connected, no battery. See, N pole is introducing here. So due to introduction of N pole, current is generated. Then here the lines of force are coming out. So from here also we will get N pole in front of the coil. So N means repulsion will be there, so it will oppose. Then the very basic rule of Lenz is, the direction of induced EMF will be such that it can oppose the cause of EM induction. Why the induction is made? Means here, why N pole? Due to introduction of N pole. So it will oppose the motion of N pole. So N pole must be induced in front of the coil. And from this we can explain conservation of energy. And from conservation of energy we can find out Lenz law also. That I have discussed previous class. Now, whenever this is a magnetic field, whenever a conductor is moving with certain velocity in magnetic field, so during motion it will cut the flux here, because flux are behaving like elastic string. So elastic string is going like this. Now when it is going perpendicularly, it will cut the field lines. And whenever it will cut, as well as the electrons present here, that electrons will experience force due to the magnetic field lines, and it will goes in a particular direction. Let here, this direction, electron is concentrated. So electron is concentrated here, means negative, here it is positive. That means we find the potential difference between two ends, that is EMF is induced. So during this motion, it will cut the field lines, as well as the electrons deflect in a particular direction, and we will get potential difference between two ends of the conductor. Now, what is the amount of induced EMF? We know E equal to d phi dt. Then we can write here phi means B into A. B is the magnetic strength of this field, whatever I have applied. So B dA dt, that is B ddt of A means L into X. L is the length of the rod and X is the distance covered. What is the distance covered? So here we can write B L dx dt, and dx dt is nothing but the velocity, BLV. So this is the amount of induced EMF. Now here I have considered the conductor is moving perpendicular to the field, but it may not. If parallel to the field, then 0, because it cannot cut the field lines. If it is going like this, parallel to the field, it cannot cut the field lines. So by making certain angle, then we have to consider here the sin theta, because the sin theta component remains perpendicular to the field and it will help to cut the field lines. So here we can find out BLV sin theta, that is E equal to L into V cross B. So the direction of induced EMF is given by the great scientist Fleming's, because in last chapter also we have direction, we got direction of deflection from Fleming, here also from Fleming. So Fleming said that if we stretch our first three fingers of right hand mutually perpendicular to each other, then if this forefinger indicates magnetic field and this indicates the direction of motion, then this will be the induced EMF. So this is the magnetic field, this is the direction of motion, this is the induced EMF. So this is the law through which we can understand the direction of the induced EMF. Now, instead of linear motion, if the conductor performs circular motion, then what will happen? Circular motion, like this, the rod is moving. So that time also we can consider a small element dx at a distance x, and then induced EMF B equal to B L V. And here we can transfer that V means omega x, omega r. So E equal to B omega 0 to L x dx, that is half B omega L square E equal to. So this is due to rotation of the conductor, and this is that previous one, this is the linear motion. Similarly, if a coil rotates in magnetic field, it will produce induced EMF. How? That this is magnet N pole, this is magnet S pole. A magnetic field is developed here. Now a coil is rotating. Okay. So whenever this coil is rotating, that just you can consider this is the coil. Here the turns are made. So you can consider this is the plane of the coil. So when the plane of the coil remains perpendicular to the field lines, then the striking amount of flux is maximum. But when it is turning and becomes this, then flux is 0, parallel to the field. So during rotation, it will cut the field lines always. Means the magnetic field lines related with the plane of the coil, where turnings are made, will change always, and flux change always gives us the induced EMF. Then here we have to find out the flux. Flux is N B A cos theta. If the plane of the coil makes an angle theta with the field, then this. So N is the number of turns present here, and B is the magnetic intensity. A is the area of the coil where turns made. Okay, turns are made. Now we can modify here that N A B cos omega t. Now take the derivation d phi dt, that is N A B omega sin omega t. Fine. So this is a constant term, which is the maximum EMF, because sin value is 1. So minus E0 E equal to E0 sin omega t, because this is E equal to minus d phi dt. That's it. So these are the facts I have discussed earlier. They get again repetition. So most of the numericals related with this part only. Now I am going to the new part. What is self-induction? Self-induction. What is this? Let this is a coil and current is sent. So we know that a coil produces magnetic flux around it, like this, the field lines and that part. Okay. So I am not giving any extra field from outside, or I am not bringing any magnet. So whenever current is given here, it will produce magnetic flux. But we know that current will get the saturated after certain time. So that time when the current varies, or you can use one rheostat to vary the current, then what will happen? Then you will get that the flux related with the coil changes. So when flux changes, it will induce EMF, and which will oppose the growth and decay both. When flux is increasing, then the induced EMF will try to decrease the flux, and when flux is decreasing, then the induced EMF will try to increase the flux. So it opposes both the growth and decay of current in the circuit. Now, why it is self-induction? Because I am not giving any extra field. It produces field, own field, and with this own field, induction is made. So it is known as self-induction. Now, let instant the current is I. So flux related with the coil is phi proportional to I. Then phi equal to Li. That L is known as induction, self-inductance, self-inductance or coefficient of self-induction. Okay, coefficient of self-induction, inductance, inductance. Now you can take derivative d phi dt equal to L di dt. Now this is E equal to minus L di dt. If we find that di dt equal to 1 ampere per second, 1 ampere per second, and E equal to 1 volt, then L equal to 1 Henry. So Henry is the unit of inductance. Okay, so this is the way to find out the self-inductance. Now, how we can find out the self-induction value? So here one important concept I said earlier, that due to self-induction it will oppose the growth and decay of current. So you can say that inductance is the measurement of electric inertia of a coil. So it is the just like inertia always opposes the motion. When motion is there, inertia will try to hold the motion. Means we cannot brake. And if motion is not there, it will not. It will try to remain at the rest. It will oppose the motion creation. So here also that inductance is the measurement of electric inertia. Now how we can find out inductance of a solenoid? Like this is a solenoid, and here the length is L. The total number of turns is N. So what is the amount of flux present here? NBA. This is the amount of flux present. N is the total number of turns. Now phi equal to, you know that Li, and N equal to, this is mu 0 N by Li into A, and L equal to mu 0 N square L A. So this is the value of inductance, self-inductance. So it depends on turn square. So if turns more means it will increase by square turn. So this is the way to find out the inductance. Now, whenever current is increasing the circuit, then it will oppose, the inductance will oppose the increment. So we have to perform the work against the inductance to grow the current, and that work is stored as energy. So what is the amount of energy present here? How we can find out? See, the induced EMF in the coil E equal to d phi. This is know that, or from here we have received L. Minus is there for direction. I am not going to the direction because energy is not a vector quantity, it is scalar quantity, so direction is not required. So I am not going there. I am considering the magnitude only. Now this is E. So what is the power? Power equal to E into I, that is L di dt into I, power generated in the coil. Now in dt time, what is the energy stored? Energy equal to energy dE, energy dE equal to power into time. So power is L di dt into I into time is dt. So here it is coming L I di. So this is the energy in time dt. So what is the total energy? That is L 0 to I di, that is half L I square. Just like you can say half mv square because m is the inertia, m is the measurement of inertia. Here electric inertia is L. So this is the expression for the energy stored in the coil. Now I can modify this one. How it can be modified? This is the energy expression half L I square. Half L means we have received already n square L A into I square. Just now I have discussed what is the inductance of the solenoid. Now we can modify it this way. This is half mu 0 square n square by L square I square into AL. See, here I have taken square, so I have multiplied it. And I already square is there. Now it can be written in the form of mu 0 n by L I whole square into AL. That is the value of V equal to mu 0 n I, small n. It is mu 0 n by L into I. So here I am getting V square on mu 0 is taken square is there, so mu 0 V square by mu 0 into volume of the coil. Volume of the coil. So this is the term which is known as magnetic energy density. And previously we have seen the electric energy density is half epsilon 0 E square. In electrostatic chapter, last theory of Gauss theorem, that time we have seen that this is the expression for electrostatic energy density. And this is the expression for electrostatic energy density. Okay? So these are the terms related with self-inductance. So what do you mean by self-induction? Self-induction means when current passes through a coil, magnetic field is developed around it, and due to this magnetic field, EMF will induce. If it will vary with time, then this is known as self-inductance. And self-inductance always opposes the growth and decay of current. So it is the measurement of electric inertia. And what is the value of self-inductance of the solenoid? That we have measured N is N square L. And during growth of current it will oppose, during decay of current it will oppose. So we have to perform some work to increase or decrease the current. That work is stored as energy. And what is the form of energy? Half L I square. And this can be written as half V square by mu 0 into volume of the coil. Volume of the coil. So this is the term which is known as magnetic energy density. So these are the new facts. Please practice and try to solve numericals from AC formula. It is better. And next day I will discuss about mutual induction and what is the combination of coils like that. Okay, thank you so much.